This is Marcus recording the workshop for our problem D from last homework, which is the bitwise OR operation problem, a bit of a construction. It's a problem D from the homework, by the way. So the problem asks, given integers n and k, we need to construct a sequence of non-negative integers such that they sum up to k, and the number of ones in the binary representation of a1 or a2 or ... an is maximized. So for example, given n, 2, and 3, the output is 1 and 2 because in binary representation, that's simply 1, and 2 is represented as 1, 1. And when you perform bitwise operation on these two, you get 1 and 1. And you get 2 ones, which is maximized for this problem. Now, the first thing we want to notice is that in bitwise OR operations, and when you perform a sequence of bitwise OR operations across integers, once the digit has been set in any number in the sequence, that digit will be set in final expression due to the characteristics of OR operation, where 1 or 0 is 1 and 1 or 1 is 1. So once you have a 1 in any digit, this digit in final expression will always be 1. It will not revert back to 0. Now, so given that, we notice that it's most efficient, given the constraint k, to output integers that set each digit once. What I mean by that is outputting 1, 0 is more efficient than 1, 1, because we can potentially use this 1 to attain a more significant digit, to set more significant digits, because we are under a constraint of k. We also notice that we can output trailing zeros because of the constraint that says non-negative integers. Having said both of that, our approach is to output one integer a that sets all reachable digits to 1, and another integer b such that a plus b equals to k, and then we append any trailing zeros so that they add up, so the number of integers add up to n. And what I mean by reachable is the number of digits that's attainable given this constraint k in binary form. So when we think about this integer a, what kind of integer has all ones in binary expression? And the answer is quite simple. It's any powers of 2 minus 1, where p is an integer. So 2 to the power of p minus 1, for example, 1, 3, 7, 15, 1 is 1, 1, 3 is expressed as 1, 1, 15 is expressed as 1, 1, 1, 1 in binary expression, and such. So all we need is to compute the power p and find integers a and b that add to k and append 0 if necessary. And the only edge case is when n is equal to 1, we output k, as given in the problem statement. So when we code this solution, so we include all the necessary packages. There's some unnecessary ones, but so we input the number of test cases, we input integer n and k. And this is the important part, where we compute the power of p. So this power of p is the floor of log base 2 of k plus 1, where k is the constraint. And we do k plus 1 to avoid the case where k is exactly equal to any powers of 2 minus 1, because later on, when we compute a, we subtract 1 from the problem. So the first if case handles the edge case where n equals to 1, in which we simply append k to our first sequence, and then we append 0 to the rest of the sequence. Oh, sorry, this for loop doesn't run when n equals to 1, so forget about that. So, and else, the general cases, we simply compute a given the power, and b such that b equals to k minus a, and this satisfies a problem constraint where a plus b equals to k, and we append these integers to our sequence. And then we append the trailing zeros if n is any greater than 2. And thus we get the final answer, and let's run this problem to see if we get the right solution. Okay. G plus plus, wait, G plus plus, D dot C plus plus. It's taking a while. So now it's finished. Let's try to run this. So now we see that we get different results, but they still evaluate the same number of ones in the final expression, because 31 is simply expressed as 5 ones, and any number that follows doesn't really matter, which is the same as what we have here, in which they also get 5 ones. And that is it for my explanation of problem D from homework 11 for the class CS392 competitive programming. Thank you.